Good day. Welcome to RSET online lecture series. I am Jebin Francis, Assistant Professor from the Department of Electrical and Electronics Engineering, RSET. In today's lecture, we are going to discuss about the subject EST130, Basic Electrical and Electronics Engineering. The specific topic under discussion will be relationship between line and phase voltages and current in a star-connected system. This particular lecture will be intended to first year students of all branches under KTU. Now before we move into the specific topic, I would like to give you a bird's view regarding module 3 from which this particular topic is extracted. Module 3 can be broadly divided into two sections, part A and part B. The part A and part B do have three subdivisions. In part A, we'll see the phasor representation in the beginning, and later on we shall see the analysis of a purely resistive, inductive and capacitive circuit, followed by the combinational circuit analysis in which we shall discuss about RL, RC and RLC. In part B, we are discussing about three-phase AC systems, followed by balanced star-connected system and balanced delta-connected system. So today's lecture, we'll be dealing with the second subsection of part B, balanced star-connected system. The main content of the lecture will include an overview of a three-phase star-connected system. We shall discuss about what is line and phase voltages, line and phase currents of a star-connected system, after which we shall try to derive the relationship between line and phase voltages and currents in a star-connected system. We'll see what is vectorial addition of phase voltages, and at the end we shall see the complete phasor diagram for voltage and currents in a star-connected system. We'll conclude the discussion with the summary and references for today's topic. Overview of a three-phase star-connected source. As you are aware, a three-phase electric system may be considered as three separate single-phase systems, phase displaced from each other by 120 degrees, and the peaks of their respective voltages do not occur simultaneously. The common configuration of interconnection of a three-phase system are either star or delta. Now right now we are going to see a balanced three-phase system which is connected in star configuration. Now the figure represents a balanced three-phase star connected source. Remember, it is a three-phase system, so we have separate three single phase system. So that is, one phase is R, second phase is Y and third phase is B. So here we have three separate single phase systems connected in star configuration, and they are 120 degree phase displaced. Now VRN, VYN and VBN represents the phase voltages of this star connected source. Now N is the common point, which is nothing but the neutral. Now the voltage equation of a three-phase star-connected source which is balanced is equal to VRN is V at an angle 0, VYN is V at an angle minus 120 and VBN is V at an angle minus 240. Now the figure represents the output waveform of a balanced three-phase star-connected system. You know that for a balanced three-phase star-connected system, your VRN, VYN and VBN represents the phase voltages, and they are equally displaced by 120 degrees as per the equation. Now if you look into the output waveform, I'll just redefine what is a three-phase system. A three-phase system can be defined as a separate three single-phase system. So you can see separate three single-phase system generating sinusoidal voltages. The three phases are R phase, Y phase and B phase and every phase is generating sinusoidal voltage, and we have two conditions to be satisfied. The first condition is that there has to be a phase displaced by 120 degrees, so it is being satisfied, and the second condition is that their positive peaks will not fall simultaneously. So if you can see in the figure, as per the equation, your R phase is starting at a 0, your Y phase is displaced by 120 degrees. If you compare R phase and Y phase, it is displaced by 120 degrees, and if you compare R phase with B phase, it is being displaced by 240 degrees. So the positive peak of R and Y is displaced by 120 degrees, and the positive peak of Y and B is displaced by 120 degrees. Now the phase displacement, the positive phase displacement of R phase and B phase is 240 degrees. Now with this, we are going to define a new terminology in three-phase system, which is called as phase sequence. Now the phase sequence is defined as the sequence in which, or the order in which, the voltages of a three-phase system attains their maximum positive value. So if you look into the figure, the order in which the maximum positive value is attained is first is by R phase, followed by Y phase, and followed by B phase. So I can say the phase sequence of the above waveform is nothing but R, Y, B. Next, we are going to see how we can vectorially represent the phase voltages of a star connected system. Now we know that the equation of the phase voltages of a star connected system is V at an angle 0, Vyn is V at an angle minus 120, and Vbn is V at an angle minus 240. So the V represents the magnitude and angle represents the phase displacement of each phase voltages. Now in order to draw the vector representation, I'll take one of the phase voltages as reference. So here I am going to take Vrn as a reference voltage, which is V at an angle 0. So I have drawn Vrn. So this is taken as a reference value. So I took this as reference. Now next I have to draw Vyn, which is V at an angle minus 120. Now in case of vector representation, remember the angle measured in clockwise direction is taken as negative, and the angle measured in the anti-clockwise direction is taken as positive. So next we have to represent Vyn as V at an angle minus 120. So I'll measure 120 degrees in the clockwise direction and I'll draw Vyn. Remember, their magnitude is same, which means that the length of Vrn and Vyn has to be same. Now the next vector which has to be drawn is Vbn, which is V at an angle minus 240 volt. So from here, which is nothing but the reference, I'll again measure 240 degrees. So 120 plus 120, I get 240. Now I will draw Vbn with the same length, which is nothing but the magnitude is same. And I have shown an arrow mark over here which represents the direction of rotation of the phases with respect to an angular speed of omega. Now from here also I can define what is a phase sequence. The phase sequence was defined as the order in which you get the maximum positive phase voltages of a three-phase system. Now if I take this as a reference, okay, this point as reference, and if this particular phasor was to rotate in the anti-clockwise direction, the next phasor to reach this particular point is Vyn followed by Vbn. So here also I can say that my phase sequences are YB. So next we are going to define what you mean by line currents and phase currents of a three-phase balanced star connected system. So we'll define what is line current first. A line current is defined as a current flowing through the line. And again the phase current is defined as a current flowing through the phase. Now we'll see a star connected system. So here a star connected system is shown over here. Now you know that Vrn, Vyn and Vbn represents the phase voltages. Now if you take up this particular picture, the portion from here to here, it is called as the face. So you have three faces, R, Y and B. So from here to here, it is called as the face. Now this part of the picture is called as the line. Okay, so through the line, the current flows to the load. Okay, so I will mark the line currents first. So the current passing through the line is called as line current. So IR, IY and IB is called the line current. Now the current passing through the phase part of the picture is called as the phase current. So this is the phase and the current passing through the phase is IRN, YN and IBN. So the line currents are IR, IY and IB, and the phase currents are IRN, IYN and IBN. So we have seen from the picture IR, IY and IB represents the line current, and IRN, IYN and IBN represents a phase current of a three-phase balanced star connected system. Now what is the inference out of this? So if you compare IRN and IR, you know that it is the same, right? Similarly, IYN and IY is the same current flowing. And similarly for the B phase also, my IBN is equal to IB. So I can generalize that in case of a balanced three-phase star connected system, my line current and phase currents are the same. And there is one more additional point. For a balanced three-phase star connected system, the vectorial sum of IR, IY and IB is equal to 0, which means that if I had a neutral wire towards a load, my neutral current will be 0. So next we are going to define what I mean by phase voltage of a star connected system. Now in the previous discussions we have seen the basic equation of phase voltages, but we haven't defined it. So let us define what I mean by phase voltage. Now the phase voltage is defined as a voltage between the neutral and a line. So let us consider a three-phase system which is connected in star configuration. Now the phase voltage is defined as a voltage between the neutral and the line point. So if I take R phase, my VRN represents a voltage between the neutral and the line R. So VRN represents a phase voltage. Similarly, VYN represents a phase voltage of Y phase with the line Y. Now similarly, if I take B phase, VBN represents a voltage between the neutral as well as the B phase. So VBN is a phase voltage. So here VRN, VYN and VBN represents the phase voltages. We know the basic equation of these three, where V is a magnitude and they are displaced by 120 degree apart. So if I look into the equation, I can see that the magnitude of three phase voltages of a balanced system is the same. So I can write the magnitude of VRN is equal to VYN is equal to VBN is represented as V phase. Their magnitudes are the same, but they are displaced from each other by 120 degrees. Next, we are going to define what we mean by line voltage of a balanced star connected system. So let us define what is line voltage. Now the line voltage is nothing but the voltage between two lines are called as line voltage. Now if you consider a three-phase system which is connected in star configuration, you know that VRN, VYN and VBN represents the phase voltages. Now the line voltage is defined as a voltage between two lines. So here VRY represents the line voltage which is between R and Y. Similarly, VYB is a voltage between Y phase and B phase. Now again VBR is nothing but the voltage between the lines R and B. So from the figure it is clear that VRY, VYB and VBR represents the line voltages, which is represented by VL. Now there is one more additional information. So VRY is a voltage between R and Y phase. So I can relate VRY in terms of phase voltages VRN and VYN. I can say that my VRY is a vectorial difference of VRN and VYN. Similarly, for VYB, it is a vectorial difference between the phase voltages of Y phase and B phase. Now similarly, my VRB, which is nothing but the line voltage, is a vectorial difference of phase voltages of B and R respectively. So next we are going to derive the relationship between line and phase voltages of a star connected system. For that we will be doing vectorial addition of phase voltages. Now we know that VRY is equal to VRN minus VYN, or else I can write VRY is equal to VRN plus minus of VYN. So we'll represents the phase voltage initially. So my VRN, VYN and VBN represents the phase voltages of a balanced star connected system, and this is a phasor representation. Now we are going to perform the vectorial addition of these two vectors VRN and minus VYN. So we'll draw minus VYN and we are going to add this. So here I am going to do parallelogram law of vector addition. So this angle is 60 degrees. You know that the angle between VRY and VBN is 120 degrees. So exactly half of that you get 60 degrees. Now I'll complete the parallelogram and my resultant will be VRY, which is at an angle 30 degrees with respect to the reference. So we'll try to find what is the magnitude of VRY. So the magnitude of VRY, we'll apply parallelogram law of vector addition, which is equal to VRN square plus VYN square plus 2 VRN VYN cosine of the angle between the two vectors. So if you look into the figure, the angle between the two vectors under addition is 60 degrees. So I'll just simplify. You know that VRN VYN represents the phase voltages. So I'll represent everything in terms of phase voltages. So magnitude is same. The cos 60 is 1 by 2. So if I were to simplify, I get VRY is equal to root 3 V phase, which is nothing but my line voltage is root 3 times the phase voltage. So this is obtained through vectorial addition of phase voltages. So with this we found out what is the magnitude of the line voltage of a three-phase star connected system in terms of phase voltage. VRY is equal to root 3 V phase. So we derived VRY is equal to root 3 V phase. Now similarly, if I were to apply the vectorial addition for the other line voltages VYB, you know that VYB is equal to VYN minus VBN. Again, I'll get the same result as root 3 V phase, and that is applicable for VBR as well. So in general, I can say that my line voltage is equal to root 3 times the phase voltage in case of a balanced three-phase star connected system. Now we'll see what is the angular displacement of VRY with respect to VRN. So the figure represents the phasor representation of a three-phase balanced star connected system where VRN, VYN and VBN represents the phase voltages. So here you can see that these three phases are rotating in the anti-clockwise direction with an angular speed of omega. So if I were to find the angular measurement of VRY with respect to VRN, I can say that my VRY is 30 degrees ahead of VRN, which means that my line voltage is 30 degrees ahead of their respective phase voltage. The line voltage is 30 degrees ahead of their respective phase voltage. Now we are going to draw the complete phasor diagram of a balanced star connected system representing phase voltages, line voltages and line currents. So that will be completed in 5 steps. So we'll go in step-by-step procedure. So here I am going to draw the phasor representation of the phase voltages initially in step 1. So we know that our VRN is V at an angle 0, VYN is V at an angle minus 120 and VBN is V at an angle minus 240. So next we shall draw VYN. Remember, the angular measurement in the clockwise direction is taken as negative and angular measurement in the anti-clockwise direction is taken as positive. And this represents that the phasor is being rotated in anti-clockwise direction with the speed of omega. So I'm going to take VRN as a reference, which is at 0 degrees. Now I have drawn VYN measuring the angle 120 in clockwise direction. Now next I'll draw VBN, which is equal to V at an angle minus 240. So from here the reference vector I'll measure 240 degrees and I'll draw VBN. So you can see that all the phase voltages in case of a balanced star connected system is equally displaced by 120 degrees. So this is 120 degrees. Again, difference between VYN and VBN is 120 degrees. Again, the angular difference between VRN and VBN is 120 degrees. So in step 1, we represented the 3 phase voltages of a balanced star connected system. Now in second step, we are going to represent the line voltages of a balanced star connected system. So you know that the line voltage VRY is equal to VRN minus VYN. So we'll perform vectorial addition and we'll draw VRY, which is nothing but the line voltage. So I did the vectorial addition between VRN and minus VYN and I have drawn VRY. Similarly, we'll draw the next line voltage VYB, which is equal to VYN minus VBN. So this is my VYN and I'll draw minus VBN and I will complete the line voltage VYB. Similarly, I'll draw the third line voltage represented as VBR, which is equal to VBN minus VRN. So this is my VBN. I'll draw minus VRN and I'll complete the parallelogram law of vector addition and I'll obtain the line voltage VBR. So if you look into the figure, one thing is very clear that the line voltage is 30 degrees ahead of their respective phase voltages. So our VRB is 30 degree ahead of VBN and again the line voltage VYB is 30 degrees ahead of VYN. Remember, all these phasors are rotated in anti-clockwise direction with a speed of angular speed of omega. Now in step 1 we have represented the phase voltages of a balanced star connected system. In step 2 we have represented the line voltages of a balanced star connected system. Now in step 3 we are going to measure the angular displacement of the line voltages. So if I were to measure the angular displacement, I can say that my line voltages in case of a balanced 3-phase star connected system is equally displaced by 120 degrees. The line voltages are 120 degrees apart from each other. Now, in step 4, we are going to represent the line current in a balanced three-phase star-connected system. So, we are going to represent the line current. So, first line current I am going to represent is IR. Let us assume the line current IR is lagging the phase voltage by an angle phi. Similarly, that will be the case with respect to IY and IB. So from the figure you can see that all line currents are lagging the voltage by an angle phi. IR is lagging the voltage VRN at an angle phi. Similarly, I can say that VBN is leading the line current by an angle phi. Again, here also I can say that my IY is lagging the voltage VYN. Remember, this is being rotated in the anti-clockwise direction with an angular speed of omega. So that's why we say this is lagging the voltage. Now, if I go to measure the angular displacement with respect to IR and VRY, it is nothing but 30 plus phi. So I can conclude that in case of a balanced star connected system, the angular displacement between the line current and the line voltage is 30 plus phi, where the currents are lagging. Now, in step 5, we conclude the complete representation of phasor diagram of a balanced star connected system. So here we have represented the phase voltages initially VRN, VYN and VBN at an angle 120 degrees. After that, we have drawn the line voltages VRY, VBR and VYB. And the third step, we have represented the line currents. We assumed the line current is lagging the phase voltage by an angle phi. So there are different conclusions which we made in each step. The first conclusion was that our phase voltages are equally displaced by 120 degrees. The second conclusion was that our line voltage is equally displaced by 120 degrees. The third conclusion was that the line voltage is 30 degrees ahead of their respective phase voltage. Now the last conclusion was that the angular displacement between the line current and the line voltage is nothing but 30 plus phi. Right now, we'll just summarize the points which we discussed in case of a balanced star connected three-phase system. So as we have seen from the phasor representation as well as from the connection diagram, the line current and the phase current in a balanced three-phase system, star connected system, is equal. Now regarding the line voltage and phase voltages, you can see the phase voltages are 120 degree apart from each other. Similarly, our line voltages are 120 degree apart from each other. Now we shall see what is the magnitude as well as the direction of line voltage. Now we have seen the line voltage is root 3 times the phase voltages from the derivation, and again the line voltages are 30 degree ahead of their respective phase voltages. That is, VR will be 30 degree ahead of VRN. Now to conclude, the angle between the line current and the corresponding line voltage is 30 plus phi, where phi is nothing but the angle by which the line current is lagging the phase voltage in a balanced three-phase star connected system. Now these are the references for today's topic: Engineering Circuit Analysis by Heath, or Electrical and Electronic Technology by Hughes, or circuit theory analysis and synthesis by Chakrabarti. In the next lecture, we shall discuss about delta connected system in detail. Thank you.